Hi guys, hope you're having a wonderful day so far. We're going to continue our chapter 6 notes, and we are going to talk about two more properties and their trends on the periodic table. So the two properties we're going to talk about today are metal reactivity and ionization energy. So as always, we're going to start by kind of defining what these properties mean. And so we're going to start with reactivity. What is reactivity? Well, reactivity is the tendency to undergo a chemical change. So let's write that down first. Tendency to undergo chemical change. And if you remember, chemical changes occur by the transfer of electrons. So when electrons are lost or gained or shared, that's what causes chemical reactions, specifically valence electrons. So it turns out metals and nonmetals tend to behave a little bit differently. And so let's take a look at our periodic table. So the metals on the periodic table are on the left side. The nonmetals are on the right side. So let me put up a periodic table right here for you. So remember that the stair step is what separates the metals from the nonmetals. So these are all metals on this side. These are nonmetals on the other side. So metals are here. Now let's look at their valence electrons. So let's start with group 1. Group 1 has one valence electron, right? Group 2 has two valence electrons. Transition and intertransition metals all typically have two, maybe one valence electron. A few metals have a few more valence electrons, like aluminum has 3, lead maybe has 4, but the majority of metals tend to have 1 or 2 valence electrons, so just 1 or 2. Now remember that atoms bond in order to achieve a low energy configuration, a stable electron configuration, like noble gases. And so noble gases have these filled sublevels, which makes them low in energy and stable. And so all the atoms want to bond and react in order to achieve a noble gas configuration. Well, if you only have 1 or 2 valence electrons, you could do one of two things. So let's look at sodium, for example. Sodium has 1 valence electron. So if it wants to become like one of the noble gases, it could either lose that 1 valence electron to become like neon, or it could gain 7 to become like argon. Well, which one's easier, do you think? Losing just 1. Same thing with group 2. They have 2 valence electrons. Easier to lose 2 than it is to gain 6. And so metals, because they only have typically 1 or 2 valence electrons, very, very few valence electrons, they tend to lose valence electrons, give away their valence electrons to achieve a noble gas configuration. And so that's how metals react. They react by losing electrons. So let's write that down. Metals react by losing electrons. And when they lose electrons, of course, they become positively charged. Now, electrons, the reason why electrons are held in the atom, as opposed to, like just flying off, they are there because of the attraction to the nucleus. Remember Zeph, the net Coulombic attraction between the nucleus and the valence electron. So these electrons are attracted to the nucleus. So think of like two magnets attracted to each other. In order to remove one magnet from the other, in order to remove two things that are attracted from each other, you have to put in energy. And the more the attraction, the more energy you have to put in. And so basically that's what ionization energy is. The valence electrons are attracted to the nucleus. And so in order to remove those valence electrons, in order to lose those valence electrons, we have to put in energy into the atom to remove those valence electrons. That energy that's required to remove the electron is ionization energy. So let's define that. Let's write it down. So it is the energy required to remove the outermost electron from a gaseous atom. And again, we have to put in energy in order to remove the electron because that electron is attracted to the nucleus. So we have to overcome that attraction and pull it away. The units for ionization energy, it is an energy, so it's usually measured in joules or kilojoules. Joule is a very small unit of energy, so usually it's in kilojoules, and a lot of times you'll see it in kilojoules per mole. We'll talk about what a mole is when we get to chapter 10. So if we were to look at some Aufbau diagrams for some elements here, we have magnesium, calcium, and aluminum. I already went ahead and drew the Aufbau diagrams here to show you. So magnesium and calcium, you know that they are in the same group. Calcium is below magnesium on the periodic table. Magnesium and aluminum are in the same period. So I thought we'd pick one from each, like two that are in the same period and two in the same group. And I want you to think about it. What do you think? Which one is the most reactive and why? Magnesium, calcium, or aluminum? So please stop the video, think about it, and then resume the video after you've thought about it. So hopefully you've stopped for a minute and thought about whether magnesium, calcium, or aluminum is the most reactive. And now we're going to actually carry out these reactions and look to see which one is the most reactive. So I have here 3 test tubes. They all have some water in them, just plain water. And I also added a drop to each of them of phenolphthalein. Phenolphthalein, you probably have used that in biology last year if you've taken biology. It's an acid-base indicator. It really does not add anything to our reaction that's going to happen, but it does show us if a reaction does happen, because one of the products, if a reaction happens, is going to be a base. And phenolphthalein, as you can see in water, is colorless. But if a base forms, then it's going to turn pink. So these are not very big reactions, and so we'll be able to tell if a reaction happens from the color. So I'm going to add a piece of aluminum to the first one here. So you can kind of see there's not much happening. We'll leave it for a minute, see if anything changes. The next one, so that was aluminum. Next one's magnesium, so I'm going to take a piece of magnesium. Remember, magnesium comes in a ribbon. I'm going to cut a piece, and I'll cut this piece into smaller pieces. That way they're more exposed, more surface area, so they can react faster if a reaction is going to happen. So I'm going to drop these into my second test tube here. Again, we're not really seeing much happening, so I'll leave it for a minute. Oh, maybe something is happening. Let's see. I don't know if you can see that I'll fold it against my shirt. 2 of them. I don't know if you can see there's a tiny bit of pink in here. Compared to this one, nothing really is happening at all. We'll leave it again for just a minute and look at it again. I'll do calcium in the other one, so here's my calcium. Put a chunk or 2. Ooh, that one immediately you see fizzing happening. A gas is forming, and you see definitely it is pink. So out of these 3, it looks like calcium is definitely the most reactive. Let's look back at the other 2. Hopefully you can see that magnesium is a little bit more reactive. I'm going to get something white for the background here. Maybe this will help you see it better. So calcium is the one that's over bubbling right now. It's very reactive, relatively. Aluminum is in the middle, not doing anything at all. And then magnesium is right here, and you can see there's a little bit of pink happening there. So it looks like calcium is the most reactive, followed by magnesium, and then aluminum is not reactive at all. Now, if you think about that, that should make sense. If I were guessing, I would have probably guessed that aluminum is the least reactive, because where do we use aluminum? Aluminum foil, right? We wrap our food in aluminum all the time. We don't want our food is mostly water. It has water in it. We don't want the aluminum foil to react with our food, right? So I would have predicted that aluminum would be the least reactive. I probably wouldn't be very sure about the calcium and the magnesium. I guess there is magnesium in your body. I don't know if you know that. There's definitely calcium in your body and your teeth and your bones, but that's a calcium compound. It's not elemental calcium that we're talking about here. So it looks like we have a trend here, but let's also test a few more. So I'm going to test lithium, sodium, and magnesium next. In your packet there's room for you to write all these observations for all the 6 metals that we're testing. So I'm going to do the same thing, but in a beaker now. So I have some water here, and I have some phenolphthalein in the water, and I'm going to add just a tiny piece of lithium to it. Now, alkali metals, we usually keep in kitty litter to absorb any moisture, and then it's also kept in oil to prevent it from reacting. And try to pull a piece here. It's kind of difficult. Huge chunks. Okay, so I got a piece right here. And I'm going to use a watch glass to show you here. So it looks pretty dark. Alkali metals are pretty soft. You can cut them with a knife. And the lower you go down the group, they get softer and softer. I don't know if you can see this, but it's pretty shiny on the inside. The outside is pretty dull and dark. That's because of the oxidation, but the inside is very shiny. So I'm going to cut another small piece here, and I'm going to put the rest of it back in my container. And then I'm going to drop that piece that I cut into the water. So hopefully you're able to see this. And hopefully you can see immediately we see pink, and you see a lot of smoke here. It's moving, bubbling pretty vigorously, more so than the calcium did. It's also producing hydrogen gas. And so you can hear it, you can see it. It's pretty reactive. Again, even more reactive than the 3 that we've tested. So I'm going to next test sodium. So same thing, I'm going to get a beaker that has water in it and also has some of the phenolphthalein indicator. I'm going to take a piece of sodium out. Let's see if I need to cut it. This one's pretty small, so I think it's okay if we don't cut it. And I'm going to go ahead and put that piece in the water. And I want you to notice whether it's more or less reactive than the lithium we saw. So what do you think? Oh, look at that, flame. Definitely more reactive than the lithium we saw. So it looks like sodium so far is the most reactive out of all of them. So going. And finally, I'm going to take another beaker, and again, it just has water and phenolphthalein in it. And next, I'm going to try some potassium. I'm going to move this out of the way. Notice also the flame with the sodium was an orange color, right? Remember flame tests when we did them? Sodium was orange. Okay, so we'll try potassium. go, small piece. It's a very tiny piece. It's actually smaller than the sodium or the potassium or the lithium we've tried, but we'll see what it does. There we go. Instantly you see a flame. Notice the color of the flame. Do you hear that? Way more reactive than the sodium. I put a very, very tiny piece, like probably less than half of what I put of the sodium, but yet you saw a flame instantly, reacted pretty violently. And so potassium, out of all of these, seems to be the most reactive. So let's go back to our notes here and see if we can explain what the trends are and why they are the way that they are. So let's answer these questions here. It's asking us which element, magnesium or calcium, is more reactive. So we saw, back to our test tubes, this was the calcium, the one that bubbled a lot. This was the magnesium. Tiny bit of reaction happening. So which one's more reactive? Looks like calcium is more reactive. Okay, so the answer here is calcium. Which one has a larger ionization energy? So let's think about this. So metals, all these metals that we've tested, they react by losing electrons. The energy that's required to lose that electron is the ionization energy. So if it's pretty easy to lose an electron, that means I don't have to put in much effort to remove it, right? Pretty easily loses the electron. So the ionization energy would be less. So the more reactive it is, that means the easier it is to lose that electron. And so because it's easier, it requires less energy to remove that electron. So the ionization energy would be less. If it is hard to get it to react, that means it's pretty difficult to remove that electron. So if it's hard to remove that electron, that means it requires more energy to remove the electron. Your ionization energy is higher. So out of those two, calcium seemed to be pretty easy to react. Magnesium was harder to react, and so magnesium required more ionization energy. So magnesium has a larger ionization energy. Let's look at question number 2. It's comparing potassium. That's the very last one that we did, that we saw the instant pink flame. Remember, potassium with the flame test was pink, right? So we saw an instant flame was the most reactive out of all of them, versus calcium, the one that was in my test tube here that bubbled a little. And so potassium is definitely more reactive than calcium. And then the next question, which one has the larger ionization energy? Well, the one that has a larger ionization energy, that means I have to put in a lot of energy to get it to lose the electron. So it's harder to get it to lose the electron. And so it's less reactive, hard to get it to lose. And so that would be my calcium here. So we want to state the trend in ionization energy across a period and down a group. We also need to state the trend in reactivity of metals across the period and down a group. Notice that I have reactivity of metals, and metals is in all caps because metals react differently than non-metals. In the next lesson, we're going to learn about non-metal reactivity, which is the exact opposite of metal reactivity. So we're focusing on metals right now. So let's look at what the trend is. So we have tested, let's look down a group first. So we've tested the lithium, sodium, and potassium. From your notes and your observations, it looked like as we go from lithium to sodium to potassium, as you go down a group, my reactivity is increasing, right? I'm getting a bigger and bigger reaction. So metal reactivity is increasing down a group. What does that mean in terms of ionization energy? Well, if it's getting easier and easier to react, that means it's getting easier to remove its electrons, so less ionization energy. So the ionization energy is actually decreasing. So they're kind of the opposite. So As I go down a group from lithium to sodium to potassium, it looks like it's getting more reactive. My reactivity of the metals is increasing, which means that it's easier to remove its electrons, so it's requiring less energy for it to react. Let's look at why that is the case. So looking back at our off-bar diagrams, let's compare to where we're going down a group. So let's compare magnesium with calcium. Remember those are these right here. Calcium is more reactive than magnesium. So if you look at the valence electrons in calcium, they're in the 4s. You look at the valence electron in magnesium, they're in the 3s. So it looks like as you go down a group, your valence electrons are in higher energy levels, right? They're farther away from the nucleus. So they're experiencing less attraction to the nucleus, right? There's more shielding, more electrons in between them, in between the nucleus and the valence electrons. So the more you go down a group, the farther the valence electrons, because the electrons are added to additional energy levels, so they're farther away, so there's less ZEF, less attraction, less net attraction between the nucleus and the valence electrons. So if there's less attraction, that means it's easier to remove that electron because there's not much attracting it, and it's going to require less energy to remove that electron. So your ionization energy would decrease. Let's write that down in our reasoning here. So as you go down a group, your valence electrons are added to additional energy levels. So remember, with all these reasons, you think about where your extra valence electrons are being added, which leads you to ZEF, which leads you to whatever the trend is for that specific property. So we talk about the valence electrons first. From there, we talk about ZEF. So because the valence electrons are added to new energy levels, they're farther away. So ZEF, which is the net attraction between the nucleus and valence electrons, decreases. So they're farther away, less attraction. So once you get to the ZEF, then you think, wait, what property am I asked about again? So let's start with metal reactivity. So metal reactivity is when you lose electrons. Metals react by losing electrons. So if there's not as much attraction between the nucleus and the electrons, is it easier or harder to remove that electron? Well, it should be easier because there's not much attraction holding it. So easier to remove valence electron, right? And so easier for metals to react. So your reactivity of metals increase. Now let's think of ionization energy. What is ionization energy? It is the energy required to remove that electron. So let's think back to ZEF. We just said that ZEF, the net attraction between the nucleus and the valence electrons is less, not much attracting, so easier to remove the electron, so it would require more or less energy. Well, if it's easier to remove the electron, then I don't need much energy to remove it. So less energy required to remove the valence electron, and so therefore ionization energy decreases. So I'm going to tell you something. I don't remember all these trends. They're all increases and decreases. If you tell me, hey, calcium and magnesium, which one has higher ionization energy? I have no clue. I don't memorize these things. You know what I do? I think of the reason first, and from the reason, I come up with these trends. So I think, oh, calcium and magnesium are in the same group. As you go down a group, there's less attraction. And so that means that the ionization energy is less because there's less attraction, easier to remove that electron. So I think of ZEF And from there, I come up with the trend. I want you to try to do that. I want you to try to understand why the trend is the way it is instead of memorizing these trends, because they're very confusing because there's so many of them and they're all increasing and decreasing. So I highly recommend that you think through, where are your extra electrons being added? What does that do to Zeph? And how does Zeph affect the property you're asked about? Okay, let's look at across a period. So let's go back here, and across a period, let's see, we saw magnesium and aluminum, right? So aluminum is the one that didn't do anything at all. Magnesium reacted, definitely. What other two did we see? We saw lithium and what other two are in the same? Sodium and magnesium, right? Sodium reacted violently, right? We saw the orange flame, whereas magnesium, again, is this one, right? So not much is happening as you go across, right? Like the reactivity seems to decrease. So as you go from magnesium to aluminum, from actually sodium to magnesium to aluminum across a period, it looks like my reactivity is decreasing. What's the reason for that? So let's compare magnesium's off-bow diagram with aluminum's off-bow diagram. Well, here are my valence electrons, 3s. There's my valence electron, 3p, about the same distance from the nucleus almost, right? They're both in the third energy level, pretty close. But what's the major difference? Well, the major difference is the number of protons. Here I only have 12 protons to pull them in. Here I have 13 protons to pull those electrons in, right? And so as I go across a period, my attraction, my Zeph, increases. So the nucleus and the valence electrons are getting attracted and attracted and attracted closer and closer and closer together. Remember, your size decreases because of that Zeph. And so if there's stronger attraction as I go across, then it is harder to remove that electron from the attraction. And so because it's harder to remove the electron, it's harder for that metal to react, and it's also harder to lose the electron, so it requires more energy to react, and so your ionization energy increases. So as you go across again, as you go from sodium to magnesium to aluminum, reactivity is going down, and the ionization energy is going up. So let's write that down and write down our reasons. Let's pick a different color here. So metal reactivity decreases, ionization energy increases. You'll notice that with all these trends, down and across are opposite. Why? Because down and across, the Zeph is opposite. And remember, all of these have to do with Zeph. Zeph is your best friend this chapter, right? So let's think about this. First thing for your reason to think through is, where are my extra electrons being added? Well, my valence electrons are being added as I go across to the same energy level. So not much repulsion happening extra, right? But at the same time, I have more protons in the nucleus. And so that causes a stronger net attraction between the nucleus and the electrons. So Zeph, which is the net attraction between the nucleus and the valence electrons, gets stronger, it increases. Okay, well, if there's strong attraction, is it easier or harder to remove the electron? Because metals react by removing electrons, right? So you think, oh, well, then what happens if there's a strong attraction? Well, if they're really strongly attracted, then it's harder to remove an electron. Right? And if it's harder to remove an electron, then that means it's harder for the metal to react. So your reactivity decreases. let's think about ionization energy. Ionization energy is the energy that's required to remove the electron. Well, we said that our net attraction between the nucleus and the electrons is stronger, and so it is harder to remove the electron. So guess what? If it's harder to remove the electron, that means I have to put in more energy to remove that electron. So more energy required to remove the valence electrons, so your ionization energy is increasing. All right, I would like you to look at these ionization energies and graph them here. So you're going to graph ionization energy on the y-axis and atomic number on the x-axis, and look at your results. And if you do that, you will notice that we have some values here that we need to take note of. So if you compare the metals with the non-metals, so number 6 here, question number 6 says, note the ionization energy values for the non-metals. In general, are they lower or higher than those values of the metals? And why might this be true? Well, if you were to actually graph it, you will see that the non-metals have higher ionization energies than the metals. Why is that? Well, the non-metals tend to be on the right of the periodic table. So as you go from left to right, we said that ionization energy increases because Zeph increases. So that makes sense, right? From your prior knowledge, we know that non-metals have lots of valence electrons, right? They tend to gain electrons than lose electrons. So for them, it would not be favorable to lose an electron. So it actually requires a lot of energy to get them to lose these electrons. But in terms of this question, I'm happy with you answering, saying, well, the non-metals are on the right side. So as you go from left to right on the periodic table across the period, ionization energy increases because your attraction increases. The last question here asks you, what are the peaks and what are the valleys on the graphs? And so if you were to graph these, you'll find that your highest points, your peaks on the graph that are at the top of the graph there, are going to be your noble gases. So they have the peaks, they have the highest values. And the valleys, the lowest numbers, are going to be your alkali metals, group 1. So why might that be? Well, that should make sense based on what we just talked about. The alkali metals are the ones that are the most reactive of the metals, right? They're the ones that easily lose electrons. Alkali metals are so reactive, remember, we have to keep them in oil to prevent them from reacting. So because they're so easy to react, that means that they require very little energy to remove their electron. They readily lose those electrons. Not much attraction between the nucleus and the electrons, very easy to remove the electrons, and so they have very low ionization energy. So it makes sense that they would be the valleys, the lowest numbers. The peaks, which ones are the peaks? Well, the noble gases. Why is that? Well, as you go from left to right, like we said, across a period on the periodic table, your ionization energy increases because Zeph increases, the attraction increases. And the noble gases are the very last group on the right, so that makes sense. But also from your prior knowledge, you know that noble gases are very unreactive, right? So it is very hard to get them to lose an electron, so it requires so much energy to get them to lose an electron, and so their values are really high. Very, very hard to get them to lose electrons and become ions because they're already stable. And again, it has to do with that attraction, that Zeph, that is very, very strong for noble gases. All right, hope this helps. In the next video, we're going to talk about 2 more properties on the periodic table and their trends. See you guys.